Hi, this is Jeff Spence, your Math 135 instructor from the Community College of Denver. We're talking about 7.1, which is titled The Distribution of the Sample Mean X Bar. So far in Chapter 6, what we did was we looked at the distribution of a random variable. A discrete random variable, such as like a binomial thing where we're counting whether a train was late or something, so that's a discrete 0, 1, 2, 3, 4, up to n, and we find various probabilities there with the binom PDF and the binom CDF. And then we can have a continuous random variable that's bell-shaped. We worked a lot with the bell curve and found probabilities and percentiles using the bell curve with normal CDF and inverse norm. Now we're going to talk, so those were two different distributions, the binomial and the normal distribution. Now we're going to talk about the distribution of the sample mean, x bar. And what's interesting about this is that a lot of students have trouble making this connection, but the sample mean itself is a random variable. Remember, if we count the number of times a train shows up late, that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we were to, if I were to do a bunch of samples of ages at CCD, before I collect that sample, I don't know what my average age is going to be of the class. Before when I asked you day one what your age was, I didn't know what the average age was going to be. We didn't know who was coming into the room that day. So I can get a bunch of different averages, anywhere from in the low 20s to say the high 30s. I bet could be an average age for a CCD class. So it is the average age, or the X bar, has a bunch of different values it can attain, maybe between 20 and 40. And it's actually a random variable. That's what we're saying here. X bar is a statistic from a sample that you don't know what it's going to be before you get it, so it can actually obtain a lot of different values. That makes it a random variable. And what we're going to find, which is really cool, is that the sample mean normally follows, the distribution of the sample mean, it can be, say, anywhere from 20 to 40, but normally it's normally distributed. It's distributed like a bell curve. So, an average age of 25 or so would usually be the most common, but we can get ages below 25 and above 25. So that's really cool. It's a continuous random variable. Now, the main things that we need to know are what's in orange here. Okay, in blue I say the distribution of all possible sample means, any sample mean you could have got, average age say. The mean of the distribution of sample means, this mean right here, the mean of the means. So the mean of all possible X bars, that's why we have the subscript X bar, is equal to the population mean. Hopefully that makes sense, but we're going to do an activity in class with the classwork where we're going to show that that the sample means, the mean of all the sample means is actually basically exactly the same as the population mean. It's really cool. And then also the standard deviation of the sample means down at the bottom is equal to the old standard deviation, the population standard deviation, I should have wrote that in, population standard deviation, divided by the square root of n. And really, folks, this is the main thing that's new in 7.1. The standard deviation is divided by the square root of n. So before we do a z-score, we got to make sure that we adjust that standard deviation. And sometimes people will see the z-score formula like this now. You'll say z is equal to, now we're looking at a data value as a statistic in x bar, minus mu over sigma divided by the square root of n. And the reason x bar comes first is that's the statistic now. That's our data value. We're going to look at the distribution of a mean as opposed to the distribution of a data point. So they got to keep that in mind for our examples coming up. The standard deviation is always divided by the square root of n, and x bar, our sample mean, is our data value. Okay, for our first example, let's look at the SAT again. The SAT is normally distributed with a mean of 500 and a standard deviation of 100. But now this time we're going to talk about randomly sampling 25 East High students. Okay, so we don't know what students they're going to be or what scores they're going to get. We want to find the probability that the X bar from this sample of 25 students, the mean of the 25 students, is at least 600. Well, the main thing that I would do first, is jot down the mean of the distribution, which is 500. Okay, the mean of the X bars. That's the same as the population mean, which is really good. I mean, that's pretty easy to translate. But the standard deviation of the X bars is the old one, which is 100, divided by the square root of the sample size, which is 25. That's from this last page here, this formula right here in red, the population standard deviation divided by the square root of n. So 100 divided by the square root of 25 is 100 divided by 5, which is 20. So the new standard deviation is 20. So in order to do this problem, we should draw the picture. What are we talking about when we're saying at least 600? Put the mean in the middle, which is 500. And 600 is to the right. And we're talking about at least 600. So that means the probability of getting 600 and above. All right. So once again, just do a z-score. Main difference here is that the standard deviation is now 20 and not 100. So we say z. We want the mean to be 600 or above minus 500 divided now by 20. I already did the side work of the division, so I'm not putting in the 100 divided by the square root of 25 down there. It's just easier that way. And you'll get a z-score of 5, I believe. 100 divided by 20 is 5. That's really high. So the chance that a East High, the sample of 25 East High students is 600 above will be the normal CDF of 5 to E99. And if we press that into our calculator, we get 2.8710 times 10 to the negative 7th, which basically means it's almost impossible to get an average of 25 students to be higher than 600. That hopefully makes sense because 600's, it's one standard deviation above the mean for one. It's not really hard for one person to get above a 600, but when you're talking about the average of 25 students, that's a big sample group, and that it reduces the standard deviation to 20, which makes a 600 as an average really, really high. Okay, so the probability for an average of 25 people to get 600 is really, really low. Okay, for the second example, we're going to stick with the SAT. It has a mean of 500, standard deviation of 100, but also, let me check real quick. Also, we're going to sample 36 East High students instead of 25. So, first of all, we want to find the probability that the sample of the 36 students, the sample mean, is at most 450. Well, first we need to jot down the mean. That's the same as the population mean, 500. But the standard deviation this time will be the 100 divided by the square root of 36 this time because the sample size is bigger. So 100 divided by 6, type that in, 100 divided by 6. And we get 16.666 repeating. Okay, so 16.6 repeating, or you could call it 16.6666, or a 7 at the end. Okay, then to do this probability, draw the bell curve, put 500 in the middle, and then we want to know 450, and at most 450. So what does that most mean? Up to. So we want to find this area here. That's the probability. Okay, so what do? Z-score. Z-score for that observation is 450 minus 500 over the new standard deviation, 16.6667. Plug that in, and we get negative 2.9. Oh, this is going to round up to 3. Sorry, negative 3. All right, so do the normal CDF. Of negative E99 to negative 3. Plug that in. 0.0013. So the probability that an average of 36 students SAT is at most 450 is 0.0013. One more example to go. Okay, for our last example, we're still with the SAT. This time we're going to sample 16 students. And we were supposed to find the cutoff for the top 10%. So what score? Find the score, that represents the cutoff for the top 10%. I should have put that in there. Find the score. okay, that represents the cutoff for the top 10%. Okay, so remember, we need to write down the mean and the standard deviation to do this. The mean is still 500, and the standard deviation now, since we sampled 16 students, is equal to 100 divided by the square root of 16, which is 4, so 100 divided by 4, 25. We have a new standard deviation of 25. Okay, draw the bell picture, put 500 in the middle, and we're looking for the score, the actual score on the number line that represents the cutoff for the top 10%. Top 10% is on the right, also known as the 90th percentile. So the top 10%, we're looking for this score. We don't know what it is. It's going to be above 500. That's about all we know. That represents the cutoff for the top 10%, which is the same as the 90th percentile. Okay, so if we know the areas, this is where we use inverse norm first. So we do inverse norm of the left area, which is 0.90, not a 0.10. Inverse norm of 0.90. Plug that in, and we get 1.2816. Now we know the z-score for this observation. The z is 1.2816. We just need to figure out the x value. So we follow our formula. X is the mean plus z times the standard deviation, which is 25. So we say x is 500 plus the 1.2816 times 25, not 100, remember. Plug that in, and we get 532, and I'm just going to round it to that because I'm running out of room. 532 as a SAT score. So if you sample 16 students, to score in the top 10% on that test, the average of 16 students needs to be 532 or more. Now, just remember in these examples, all of these examples, the only thing that's different from Chapter 6 that we just did is this new standard deviation that's circled here at the bottom in red. I did that every time in every problem. I found the new standard deviation, I'm circling it right here, divided by the square root of n. That's the only new thing. Everything else is the same. We're asking the same type of questions, at most, at least, cutoff for percentages. So the first two are for probability, and we use normal CDF. The last problem asks for a score that is a cutoff, so we start with inverse norm, use our formula to get x from z. Good luck with your examples, and we'll talk to you later.